Hello guys, in this video we shall be talking about the essentials of electrostatics, so some of the basic formulae as well as concepts that are used in certain problems in electrostatic situations. So let's begin. So the first topic is Coulomb's law. It is sort of a very simple topic that was already introduced in 12th grade and it just comes back as the initial concept in the sense that in discrete charge situation this is very useful. So this expression is very familiar to most of us, so there is no need to really go in depth. Then we have the idea of electric field. The expression here is specifically for the electric field due to a continuous charge distribution, and that is sort of the more general case, and so this is more applicable in many general scenarios as well. Then there's a new idea where we introduce the vector calculus concepts for expressing properties of the electric field such as divergence and curl. So here we assume the curl of the electric field to be 0 for certain reasons, and the divergence of the electric field is expressed as the charge density divided by epsilon 0. And from these properties we can actually derive Coulomb's law using Helmholtz theorem, and so that is a very interesting point that can be kept in mind. Now the next topic is Gauss's law, which is again one of the more important laws in terms of problem solving because we can use it in many applications, such as finding total charge if we are given the electric field in many scenarios. Also, we can find the electric field also if there is symmetry. That's how we actually find out the electric field due to an infinite line charge or an infinite sheet, and in many other symmetric cases. Then we are introduced to the idea of electric potential. Since we say that the curl is 0 in electrostatic case, then we can actually write the electric field as negative gradient of a scalar potential. Based on that, we can actually define a unique potential difference between points because the work done in some sense is only dependent on the initial and the final points and not on the path taken. Then we can also talk about potential due to a charge distribution. So the first expression is due to a discrete charge distribution, and the second one is equivalent but in the case of continuous charge distribution, and this is just a simple summation or an integral of the normal charge potential formula which we have learned in 12th grade, which is 1 by 4 pi epsilon naught q by r. Then we talk about boundary conditions as well. What will be the change in the electric field components when we cross a boundary which has charge. So as we can see, the perpendicular component faces a discontinuity and the difference is equal the magnitude of the surface charge density divided by epsilon naught, and it will be along the direction of the normal. And the parallel components don't change because we say that the curl of the electric field is 0, so for that they have to remain the same. Then the next topic is Poisson's equation, which is sort of a reformulation of the divergence of the electric field being equal to rho by epsilon 0. We substitute electric field as negative gradient of the potential and we get this expression. Now the more interesting version is the case where it is a charge-free region, so rho is 0 in that region. Then we will get Laplace's equation, which is del squared V equals 0. This equation has many interesting properties, some of which include the average value theorem, which states that the potential at a point will equal the average of the potentials in the neighboring region, assuming we take like a sphere enclosing that point. Also, another property is that there is no maxima or minima within the region itself, and extreme values can only exist at the boundary of the region. Then another important feature is the uniqueness theorem, which will be used later on while doing separation of variables. So stuff like boundary conditions, if they are given, then we can actually find a unique potential function that can satisfy this criteria or this equation. Then we shall talk about conductors. So this is another topic that was introduced in 12th grade. So we know properties like zero electric field inside in the case of electrostatic situation. So there will be zero charge density inside just by applying the divergence property. This also means the charges can reside only on the surface and that the metallic region itself is an equipotential region because the electric field is zero. Then we can also talk about the normal component of electric field, and that will just equal sigma divided by epsilon naught, which we can derive from the discontinuity property at the boundary, as we have seen in the previous slide. Then there is the idea of electrostatic pressure, and this formula is just the most important thing, where the pressure that is experienced by, let's say, a portion of the surface of a metallic sphere due to the repulsion of the charges that are residing on that sphere, that magnitude will equal sigma squared divided by 2 epsilon naught. So this is the value of the pressure that is experienced by a small piece of charge on that surface. Then the other topic is electrostatic energy. So electrostatic energy is just the energy required to set up that system of charges, or in some sense it is the energy stored in the electric field that is generated due to the setup. So there are different formulae depending on discrete or continuous charge distribution. So in discrete case, we can calculate by taking the pairwise potentials in some sense. So we'll get the first formula. The second formula is just a restatement of the first one by grouping together terms, and this is quite useful in some sense because this can be extended to the continuous charge distribution case as well. So the continuous charge distribution case has two versions, where one of them has the charge density version and one has the electric field version. The charge density version, one must keep in mind that we will only be interested in the region containing all the charges and not necessarily the entire space. While for the case of electric field version, we will need to take entire space into account for finding the total energy. If we just take the same amount of space as we take in the first formula, then we won't get the total energy required to set up that system. So this is a common mistake that could happen. So that difference must be kept in mind where these two formulas are applicable. So these are some of the basic ideas that are involved in electrostatics. Thank you.